Bose-Einstein statistics, right? And you actually derive that from deeper principles in quantum field theory, QFT. So, something to look forward to, because it's absolutely basic. That's right. The world is built, atoms are built, with these principles in mind. So, really important. All right. Okay, so we have these four antisymmetric wave functions that we built up from energy eigenfunctions of the hydrogen atom, so that's why they're called hydrogen-like. These U's here are of the hydrogen eigenfunctions. Okay. Now, in the first three cases, the electron spins are aligned, sort of parallel with each other. Now, I'm a bit puzzled by this one, the third one, but anyway. Now, it's obvious in these cases, right? The two spins are aligned, they're both up or they're both down, so obviously aligned. But I was puzzled by this one. They seem to me to be anti-aligned, so a bit of a question mark there. So, I personally, I need to study this more. I question mark at this stage. Right? Now the total spin of these two spin systems for the first three cases, according to the textbook, the total spin is 1 unit, h, and the z components, well, as usual, they range between j plus minus j in this case 1, right? So plus minus j and 0 in units of 1. So plus 1, 0, minus 1. So okay. Now in the fourth case, you've got the spatial part here. You can just see it by inspection. That's symmetric. Right? It's not antisymmetric. It's symmetric. But if you swap the spins, so like if particle 1 had spin down, particle had spin up, vice versa, that part, spin part, is antisymmetric. All right. So the total spin of these for this fourth case is 0. Go back to chapter 7. Revise your knowledge on multi-particle systems. All right. Now, saying a bit earlier, the reason why this helium atom is considered an example of perturbation theory is the perturbing Hamiltonian, the H dashed, will be the potential due to the interaction of the two electrons. Okay? So here's your basic assumption. So now we'll have a Coulomb potential, right, between the two electrons. So here's your V term, or H dashed. It's a potential energy. So the square of the charge of the electrons, so E squared, 4 pi eta, whatever it is, and this R12. Now that's the critical part. So this is your perturbing potential, and R12. And what is that R12? It's the distance between the two electrons, electron 1, electron 2. So 1, 2, R12. Okay. So here it's just the distance between electron 1 and electron 2. So a Coulomb potential, right? Now, all four of these states are degenerate in the sense they all have the same eigen energy before the perturbation, and it works out that the first three, even when you apply the perturbation, in other words, you magically switch on the interaction between the two electrons, the first three, the first order energy shift, in fact, is 0. Is that correct? Or no? Yeah, I think it says so here. Okay. Now, the authors again they're talking about the degenerate submatrix. So you think that seems to me common sense. If you go, this is like the second, third time the textbook has talked about this. So you think that give greater details in the discussion in the first place to explain what the degenerate submatrix is and how to diagonalize and so, well, anyway. So this degenerate submatrix, what is that? Well, the perturbation matrix, that was your H-NN from earlier theory. So it was the integral of U 0 star H-hat U0 integrated over space, right? And so if it was U-M star, that was in the bra part, and the ket part was just UN, then that matrix you could consider then as an element, that integral could then be considered as the MN component of a matrix, so call that the perturbation matrix. Okay. Now, for those eigenfunctions that are degenerate, so they have the same eigenenergy, you can take you take those eigenfunctions that have the same eigenvalue, right? And the part of the perturbation matrix that uses those eigenfunctions, the degenerate eigenfunctions, that is your degenerate. Where is it here? The degenerate submatrix. It's the part of the matrix that's where the MN, if you like, they label the degenerate eigenfunctions. Okay, so it's the part of the matrix, the perturbation matrix, that's involved with those degenerate eigenfunctions. Hope that's clear. All right. Now, to clear up the problem when you have eigenfunctions that are degenerate, you may get in the correction terms for the energy, like E1, E2, you may get and in the formula for those, you get a denominator that could be 0. So you're dividing by 0, not allowed. But you can get around that problem by diagonalizing the degenerate submatrix. And if you ask why, you're going to have to wait till done linear algebra, saying several times before. Okay. Now it's just sort of thrown at you again, but it works out that that this degenerate submatrix, it's already diagonal. Okay. And that being the case, then if you make your degenerate submatrix diagonal, then that dividing by 0 problem disappears, and that's not explained why in the text. Anyway, so that's assumed. So that problem disappears, and therefore you can use perturbation theory, even in the case of degeneracy. All right. Now, again, it's just thrown at you. Now, remember, this is the second last chapter in the book, so getting towards graduate level. So that means that you can use perturbation theory for this problem, right? So that means you can plug in your H dashed, which is this Coulomb potential form here. Okay. Now, this potential here it does not affect the spins. There's no operator here that operates on the spins. It just affects the R part, the spatial part. Now it works out, again thrown at you, so I think it's saying that in the first three cases, the triplet there's no energy correction. I think that's implicit. But there is an energy gap, a change in the energy. When you switch on the interaction between the two electrons, in the singlet case, that's the case 4. It's just one of them, single case. So this is called the singlet case. The other 3 are called triplets. You do get shifts in the energy, right? So for particle 1, particle 2, the first order correction in the energy. It's just it's about 5 more lines in the next session. So yeah, I'll just wait. I'll just carry straight on in the next session.